This presentation is going to deal with the Henderson Hasselbalch equation. I'm sure that I butchered that, but it's got a lot of L's. Oh well. So the first thing we're going to do is derive the Henderson Hasselbalch equation, and then we're going to use that equation to solve buffer problems. So last class we did buffer calculations for pH the long way. It was tedious. There were a lot of steps. But now you understand exactly how these things work, which means that we're ready to introduce the shortcut. So what is the shortcut? It is so much better that the names of the people who derived it are on the equation that they came up with. I should tell you how awesome this shortcut is. So without further ado, let's derive the Henderson-Hasselbalch equation. We know the general form for an acid ionization and what the Ka is equal to. Using algebra, we can solve the Ka equation for the H+ concentration. So hydronium ion is equal to Ka, our acid ionization constant, times Ha over A-. All right, from here, if you take the negative log of both sides, note that the negative log of H+ is pH. We end up with this fun little doodad where we've got pH equals negative log of, in parentheses, Ka times Ha over A-. Now, we are going to use the log product rule, which is on the bottom right corner in red. You can see that we can split this up. So we can break off that Ka and we can leave the Ha over A- behind. That's what we're going to do. Negative log of Ka is pKa. So pH is equal to the negative log of pKa plus the log of anion over acid concentration. This is the Henderson-Hasselbalch equation. It will make your life easier. Now you can determine the pH of a buffered solution once you know the concentration of the acid and the conjugate base. Here's the thing though. Yes, you can also use it to solve for a variety of other values, right? We could solve for pKa, we could solve for anion concentration if we knew the other stuff. There's lots of mix and match in this. But there are a few underlying assumptions baked into this derivation that are not obvious at first, and we should talk about them. First one, the salt must dissolve fully for this to work at all. In other words, you have to have something that will fully dissociate and leave you with the anion. So most of the time, you will see that your salt contains a group 1 cation or a group 17 anion, and that is because they are extremely soluble species. NH4Cl is going to totally dissociate. Sodium acetate will totally dissociate. You get the idea. So that's how we meet condition 1. Second assumption, the Henderson-Hasselbalch equation uses equilibrium concentrations, which should require an ice table. But we know that the amount of change for a weak acid in most cases will be smaller than the original molarity of the acid or the conjugate base. So we don't need to worry about plus X or minus X in most cases. We can just use the approximation saying that that doesn't matter and use the concentrations given. Which brings us to point 3. Because the first two things, this is actually an approximation of the pH of the buffer. It's very accurate as long as you are above about a 90% to 10% ratio of your components. So if you go past having 90% of one thing, 10% of another, you've blown the buffer. This equation does not work. Why? Because at that point you can't use the assumption that minus X or plus X doesn't matter. You have to go back to the ice table where you have to do the entire thing with the quadratic formula in order to solve in that case. So, to summarize, this is an amazing equation. It will cut out a lot of work for you, but you can only use it if your ratio is above 10% of something, right? So we can have above 10% of anion and 90% of cation, acid, or we can have above 90% of anion and 10% of acid. Anything beyond that, it won't work. It will give you inaccurate results. Let's try to do a calculation. Determine the pH of a 250 milliliter citric acid buffer containing 10.5 grams of citric acid and 12.5 grams of sodium citrate. We have a pKa1 of 3.13 and a pKa2 of 6.40. This is a polyprotic acid. We need to deal with this polyprotic acid in a buffer solution. That's fairly common. If you take biochemistry, you will find that phosphate buffer will be your constant companion in lab. And phosphate buffer comes from phosphoric acid, which is actually a triprotic. So how do we deal with this situation? Can we use this assumption? Recall that the second pKa is 3 orders of magnitude smaller than the first. It's going much slower. And as a result, remember from looking at polyprotic acids, when we calculated how much we make of the second anion, that X value was so tiny that it didn't even affect the value of the first anion with an error. So we can apply the Henderson Hasselbalch equation to one species at a time. That's okay. It's a safe assumption. So which one do we use for this particular situation? So we're going to write out our first and our second ionization equations. And I have put what we were given in the problem, the citric acid, as green, and I've put the sodium citrate as blue. So why did I do that? I want you to visually see that we are dealing with the first one. This is the one we're going to use. Why? Because it has both that acid and that conjugate base. And remember, a buffer always has to have an acid and a conjugate base. This can get confusing for polyprotic acids, so you just need to figure out which one has both of the species that you're interested in. All right, now that we've figured out that we're dealing with this top equation, let's apply the Henderson Hasselbalch. So we take a look and it gives us the mass of citric acid and the mass of sodium citrate that we add, but that's not molarity. And the Henderson Hasselbalch equation uses molarity, so we've got to calculate molarity. Easy enough. We take our 10 grams of citric acid, we divide it by 192, which is the molar mass, and then we divide it by 0.250, which is the liters. And we get 0.219 molar citric acid. And we go ahead and we do the same thing for sodium citrate. We divide it by 214 grams. We divide again by 0.250 liters. And we get 0.234 molar sodium citrate. Now we can put this into the Henderson Hasselbalch equation. I'm just going to call it HH from now on so I can stop trying to say Hasselbalch. And when we do 3.13 plus log of 0.234 over 0.219, it's equal to 3.16. This was a lot easier than doing an entire ice table to solve this problem. Revolutionary, really. All right, let's try another type of problem. This problem comes at the information from another direction. Determine how much HCN and NaCN you need to make a 100 milliliter buffer solution with a pH of about 8.8. So the pKa is 9.21. All right, we've got some information, we can use it. So we're going to apply what we have to the Henderson Hasselbalch equation. So we put it into the HH equation. We can solve for the log of anion to acid. And I get negative 0.4, right? And we're making sure we go to the 10th place because 8.8 is to the 10th place. Now, if I take 10 to the log and 10 to the negative 0.4, I get 0.4. So my anion over acid is equal to 0.4. So you need a solution with about 4 molar NaCN per 10 molar HCN. And we can do this in a lot of different ways. We could say, I'll take 50 milliliters of 4 molar NaCN, and I'll take 50 milliliters of 10 molar HCN, and that'll make 100 milliliters of buffer solution at the right pH. Or I could do 50 milliliters of 0.4 molar NaCN, 50 milliliters of 1 molar HCN. You get the idea. The equation doesn't specify the buffer capacity, so there's many possible solutions. What has the better buffer capacity? Is it the one where you have the higher concentration or the one where you have the lower concentration? It's the one with the higher concentration because there's more moles of material to consume before the buffer is used up. All right, now this is a little bit of an aside, but it drove me nuts when I was taking these types of classes. So in biology and biochemistry, the labs label buffers with a molarity and a pH, but it's just one molarity. We know that the buffer contains acid and conjugate base. So why does it only have one molarity for the buffer label? Here's what they do. If you add moles of acid to moles of anion and you divide by the liters of buffer solution, that is what they report as the molarity of the buffer. Now, higher molarities mean that's higher buffering capacity. So the molarity gives the relative buffer capacity when you look at it, when you get that bottle in the lab. Back on track. The next topic we're going to cover is titration curves. So here are two titration curves of buffer being titrated with a base. The one on the left is a curve for an acetic acid buffer. You'll note that the pH goes up at a relatively steady rate until you hit the inflection point, which here is labeled. And the concentration of acetic acid at that point is 11% of the concentration of acetate ion. Remember that I said a buffer is used up when you only have about 10% left. Well, 11% is really close to 10%. And so after that point, the slope of that line goes way up. And in fact, it changes rapidly, and all of a sudden it's just a huge change. Once the buffer is blown, the pH will rapidly increase. In the graph on the right, we have a titration curve for a phosphate buffer. Phosphate is a polyprotic acid, so this is only one portion of the overall titration that you could do for this type of buffer. The pKa is for the second ionization of phosphoric acid, which is 7.21. We are dealing with H2PO4 minus and HPO4 2 minus. That's our equilibrium. The x-axis gives us the ratio of acid to base. Notice how the slope of these lines changes dramatically when you get to the 9:1 ratio and the 1:9 ratio, which corresponds to about 10%. The buffer is blown on either end. So we can see, I'm not just making this up. This is a real thing. We have actual data to back it up. At about 10%, all of a sudden that slope dramatically changes. Henderson Hasselbalch will no longer apply. So, in summary, the pH of the buffer can be determined using pH equals pKa plus log of anion over acid. Or, aha! I actually remember it as pH equals pKa plus log of aha! Use whatever works for you.